Hi everyone. So this video is going to be about weekly math challenge 2. So this was around 8th to 15th of February. That was when this challenge was due. So I'm going to discuss some of the problems in that challenge sheet. So we had 7 problems with multiple parts, and I'm going to select a few questions for discussion because I didn't see too many solutions for these particular questions. So the questions that we are going to discuss today are question 1b, 2a, 2b, 3b, 4, and both parts of question 5. If you have doubts in the remaining questions, you can send me a request on the channel itself, and I will make a video separately about them. The math challenge number 4 has been released yesterday, and the deadline is as usual. It is 1 week from now, which is next Monday or 1st of March. So following this video, I'll probably also make the solution video for math challenge 3 in the next few days. So let's get to it. Question number 1, part B, right? So this is, I think, a geometric inequality. Let me just check. This is in triangle ABC. We have given angle A is 60 degree. Let P be a point in the plane. Let P be a point in the plane such that PA is equal to 6. So distances of P from the vertices are given. PA is equal to 6, PB is equal to 7, and PC is equal to 10. These distances are given. You have to find the maximum possible area of triangle ABC. Find the maximum possible area of triangle ABC. Okay. So we have a point in the plane, and there is a triangle, and there is a point in the plane inside the triangle, right? PA is, I mean, it could be outside as well, but for now we'll take it as inside. PA, so this is ABC, and PA distance is given, PB is also given, PC is also given, and angle A 60 degree is given, right? And you have to somehow get a sense of the maximum possible area of the triangle. So to solve this question, we need a particular theorem, and that theorem is coming from the cosine rule. So I'll just show you. Let's say we have a convex polygon, right? Convex quadrilateral, x, y, z, u, x, y, z, u, right? Convex means the angles are not greater than 180 degree. All angles are less than 180 degree. Less than 180 degree. Now let's join the two diagonals. Let's join the two diagonals. Let's join the two diagonals. This point is O. This is U, by the way. And let's say this particular angle is theta. XOY is theta. Okay. So I'm going to make the claim that YZ square plus UX square minus XY square minus ZU square is equal to 2 times XZ into YU into cos theta. Let's try to understand what this statement means. So this is the theorem that we are talking about. So what does it mean? First of all, YZ square plus UX square minus XY square minus UZ square. So it is the sum of two side squares minus the sum of the squares of the other two sides, right? And that is equal to apparently 2 times, one diagonal is xz and the other diagonal is yu, 2 times xz into yu into cos theta. The theta is the angle between those two diagonals. So we will prove this theorem. Anytime you see a term like this, right? This is 2 times xz into yu into cos theta, where cos theta is the angle between the xz and yu lines, right? So this should immediately give you a hint that this is a cosine rule application, right? Cosine rule also, you have terms like 2bc cos a, right? If you have done your basic triangles and all, you would have seen cosine law, and that looks similar. So the idea for the proof also comes from there itself. So let's try to prove it here itself. So I'll just erase this other diagrams here, make some space, and try to convince you that this relation is correct. So what we will do is we'll just apply cosine rule in 4 different triangles. We'll just apply cosine rule in 4 different triangles. What are the triangles that we will take? Triangle OYZ, triangle OUX, triangle OXY, and triangle OZU. So in all of these triangles, let's apply cosine rule. So OYZ triangle, OYZ, right? Now notice that this angle is 180 minus theta, right? Because diagonal was a straight line. So cos of 180 minus theta, cos of 180 minus theta would be, cos of 180 minus theta would be OY square plus OZ square minus 2 times minus A square, which is YZ square by 2 times OY into OZ, right? Now this result, cos of 180 minus theta becomes minus cos theta. So multiplied by 2 OY OZ is equal to OY square plus OZ square minus YZ square. So what you end up getting here is, bring it to this side. So you end up getting a result, YZ square is equal to OY square plus OZ square plus 2 cos theta OY OZ, right? So that was the cosine rule applied to this particular triangle. So similarly, in triangle OUX, I can do a similar thing. And what I will get again is UX square is equal to OU square plus OX square plus 2 cos theta OU into OX, right? These are 2 times we have applied cosine rule for this triangle and this triangle. Similarly, I can do this triangle and this triangle as well. So I will write the results here. You can do it yourself. XY square is equal to OX square plus OY square minus 2 OX OY cos theta. And the other one is ZU square is equal to OZ square plus OU square minus 2 OZ OU cos theta. So we have these 4 times we have applied cosine rule and 4 equations we have. Now it is a straightforward matter to compute this LHS, right? We just have to sum up these 2 and subtract these 2, right? So summing up these 2, notice that you'll get OY square plus OU square. And when you subtract these 2, these terms will get cancelled, right? This term gets cancelled with this term gets cancelled with this term gets cancelled with this, and this term gets cancelled with this. So finally, this LHS will become the sum of all of these causes, right? I hope everybody is getting what I'm saying. So sum and difference, right? So actually, when you subtract, notice that when you subtract this, this becomes positive, right? So you get 2 cos theta OY OZ plus 2 cos theta OU OX plus 2 cos theta OX OY and 2 cos theta OZ OU, right? So 2 cos theta common there, 2 cos theta common there, and between OY OZ and OZ OU, I can take OZ common, and it will become OY plus OU, right? OY plus OU, what is that? That is simply UY, right? UY. So OZ into UY plus the other terms are OX common between this and this. So OX common between them, and you get OY plus OU again, OY plus OU again. So that is again YU. And again, now between this term and this term, I'll take YU common, and it will be OZ plus OX, right? OZ plus OX is simply OX, right? So it becomes UY is simply XZ. OZ plus OX is XZ, the length of the other diagonal. So you get this. So the overall thing becomes 2 times XZ YU cos theta. So that is a very useful result, as we will discover in this question. Now let's get back to the question itself. We have proved this result. Make a note of that. Pause the video. Make sure that you understand this part very clearly. I will proceed ahead and we'll try to solve this question. So in triangle ABC, let me construct triangle ABC. Triangle ABC. I know that this angle is 60 degree, and my point is somewhere such that PA is equal to 6, PC is equal to 10, and PB is equal to, I think, 7, right? PB is equal to 7, correct. So let me draw tentatively these lines. These are my lines for PA, PB, and PC. The lengths we know, so I'll just write them down here. PA is equal to 6, PB is equal to 7, and PC is equal to 10. So what we will do is we'll try to create a parallelogram where we'll use the condition that we have just now proven. So how to create a parallelogram here? What I will do is construct a line through P, parallel to AB, through P parallel to AB. Okay, so parallel line through AB, and I'll also construct a line through A which is parallel to PB. Basically, I'm just making a parallelogram. So let's make a line here which is parallel to AB. This line is parallel to AB, and a line through A which is parallel to PB. So I'll make a line like this, which is parallel to PB. And let's say these two lines intersect at E, or at D actually, and this point, let's call it E. Okay, so I have a parallelogram. This is parallel to this by construction, and this is parallel to this. I have a parallelogram ABPD, right? Great. So angle CEP, now notice CEP by construction is going to be corresponding angles because AB is parallel to PD. Therefore, this is also 60 degree. So I have angle CEP is equal to 60 degrees by construction, because I made a parallelogram here, right? Great. Let's suppose that A to C, the distance is unknown. A to C was anyway unknown. A to C was X, right? And let's say AB was also unknown. AB was Y, correct? So I'm calling this length as my Y, and I'm calling this length, I will not draw it because, let me just do it. This length is called X, AC length, right? So ultimately, what do I have to do? I have to find the maximum area of triangle ABC, right? The reason I'm doing all this, the reason I have taken this length as Y and this length as X is because triangle ABC area can be written as half into X into Y into sine of A, right? This is half 1/4 √3 XY. So triangle area is √3/4 XY because sine A was sine 60, because the angle A was 60, right? So I have to maximize the value of my triangle ABC area, right? So notice that if AB is Y, then what is the length of PD? PD is a opposite side in a parallelogram. So PD is also Y because parallelogram, right? Great. PD is Y, and PB we already know, right? PB we already know, that was given in the question. PB was 7. So what is AD? AD is also 7. AD is also 7 because it is also opposite side of a parallelogram. Great. PA also we know. So one diagonal we already know. This is 6. PA is 6. Okay. So applying the lemma to quadrilateral APCD. So let's join this. Let's join C and D. So now we have a quadrilateral APCD, if you can see. Quadrilateral APCD, right? What is special about the quadrilateral? The diagonals are intersecting at 60 degree. And if you notice, if you remember from the lemma, the theta angle in the lemma was the angle of intersection of the two diagonals, right? So again, here we have two diagonals and they are intersecting at 60 degree. See, I could have tried to solve this question by applying that lemma to triangle AB, to quadrilateral or parallelogram ABPD. But the problem is that this BD length was not known. The other diagonal is not known here. Also, the angle here is not known, right? And in that lemma, we need the angle between the two diagonals. So the better quadrilateral for us to choose is APCD, right? So applying that lemma, so you should actually go back to your notes and see how that lemma was framed, right? I will just write the result here because I know PC also here. PC is 10, right? So I know AP is 6, CD I don't know. CD actually I don't know. So let's call CD as T. CD is unknown, which is T, and I know AP is 6. So it will be opposite squares, T square plus 6 square minus this square and this square, minus 7 square minus 10 square is equal to 2 times product of the diagonals. Now, what are the product of the diagonals? 2 times AC. AC length is Rx, right? 2x. What is PD? PD is equal to AB is equal to y. And what is cos 60? That is cos 60, right? This is cos 60, which is half. So this becomes xy. So I have t square plus 36 minus 49 minus 100, right? So t square minus 113 is equal to xy. This is what I get from the lemma that I have used earlier, right? Great. Xy is equal to t square minus 113, correct. Now, we also have Ptolemy's inequality. So Ptolemy's inequality, which by the way becomes an equality in the case of a cyclic quadrilateral, says that sum of lengths of opposite sides of a quadrilateral is greater than equal to the product of the diagonals. So basically in this quadrilateral, I can say that sum of products of the opposite side, so PC into AD plus AP into CD, PC into AD plus AP into CD will be greater than equal to PD into AC. This is a standard inequality. You can find it anywhere. Now, this inequality actually becomes an equality if the quadrilateral APCD was cyclic. So in that case, you have Ptolemy's theorem, which says that sum of the products of the opposite sides of a cyclic quadrilateral is equal to the product of the diagonals. So, but we'll use this inequality here. Now we know PC is 10 and AD is 7. So this becomes 70 plus AP, A to P is 6 and C to D is T, right? So 6T is greater than equal to PDAC. So what is PD? PD is Y, AC is X, is greater than equal to XY, right? So we get an inequality here, XY is less than equal to 60 plus 70. This is my second statement, okay? So notice now we are getting multiple relations on XY, right? One is from Ptolemy's inequality, the other is from the lemma that we created by using cosine rule. And ultimately, what do I have to say? I have to say something about this xy, right? Maximum value of xy. So now it is fairly straightforward, and I can convert 1 and 2 into a quadratic in T. So quadratic inequality, because what I will do is I will replace t square minus 113 for this. So I will make it t square minus 113 from 1 is less than equal to 60 plus 70 from 2, right? So the inequality becomes t square minus 60 minus 183 is less than equal to 0, right? This is my quadratic inequality. There are very standard ways to solve it. This quadratic will always be upward facing. T square minus 60 minus 183 less than equal to 0. The value of t has to lie between the two roots of this quadratic polynomial. So t must lie between one root alpha and the other root beta. When you calculate the root, you might get a negative root, but t was the length of one diagonal, right? One side of the quadrilateral APCD. So t was the length, so it has to be greater than equal to 0. So t values must actually lie between 0 is less than equal to t not equal to. 0 is just less than t is less than one of the positive roots of this, right? So positive root of this comes out to be 3 plus 8 root 3. 3 plus 8 root 3, right? Now, if t is between this, if t is between 3 plus 8 root 3, right? So now we already have a relation saying that xy is equal to t square minus 113, right? X square is equal to t square minus 113. So what we can say is xy, or we actually have a better relation. We have xy is less than equal to 60 plus 70. So xy will be less than equal to 6 times this. So that will be 18 plus 48 root 3. 18 plus 48 root 3 plus 70, which becomes equal to 48 root 3 plus 88. So xy is less than equal to 48 root 3 plus 88, and area of the triangle was root 3 by 4 xy. So multiply this by root 3 by 4. You get 12 into 3, 36 plus 22 root 3. 36 plus 22 root 3 is the area of triangle ABC less than equal to. The equality happens when, according to Ptolemy's inequality, the quadrilateral APCD becomes cyclic. Equality happens when quadrilateral APCD becomes cyclic, and one way to write that condition is angle PBA is equal to angle PCA. You can look at the figure that we drew earlier and verify that if this is true, APCD is cyclic, and this Ptolemy's inequality is becoming an equality. So in that case, you will get area of the triangle is the maximum possible area, and that will be equal to 36 plus 22 root 3. So that is the solution of this question. It was a slightly involved question, but it had a very instructive application. Like there are two theorems that we saw. One of them was a lemma that we derived by doing cosine rule on the quadrilateral, where we had angle of intersection of the diagonals. If this angle is known, now you can derive that this square plus this square minus this square plus this square will be equal to 2 times product of diagonals into cos theta. That was one lemma that we proved. The other one was Ptolemy's inequality. So if you're unaware of that, that is a very useful statement. So that is problem number 1, slightly long. Question number 2, however, is not so difficult. Question 2, part 1. So the question says that A, B, C are non-zero reals, non-zero real numbers, reals, such that A plus B plus C, A plus B plus C is equal to 0. And it is also given that A cube plus B cube plus C cube is equal to A power 5 plus B power 5 plus C power 5. And you have to find the value of find A square plus B square plus C square. Correct. So if A plus B plus C is 0, I hope everyone is aware of the identity that in that case, A cube plus B cube plus C cube is simply equal to 3ABC. So I'll assume that you know this fact, and the proof of this is in there. Any 10th standard till 10th standard book on algebra will have this identity, right? So what we will try to do is try to understand what is the meaning of A power 5 plus B power 5 plus C power 5, and we'll try to simplify it a little bit. Now notice that since A plus B plus C is 0, C is equal to minus A plus B. So this becomes simply A power 5 plus B power 5 plus minus A plus B whole to the power 5, which is A power 5 plus B power 5 minus A plus B whole to the power 5. We'll expand this by binomial theorem, and the first and the last term of that expansion will cancel, and what you will end up having is minus 5 A power 4B minus 10 A cube B square minus 10 A square B cube minus 5 A B power 4. This is what you get. I will take minus 5AB common from here. This becomes A cube plus 2A square B plus 2AB square plus B cube. Great. I will factorize this a little more. It is obvious how to factorize this. Minus 5AB, I will take A square I'll take actually a cube and b cube together, and that will become a plus b into a square minus ab plus b square, and plus I will take 2ab common here, and that will become a plus b among the two middle terms, these two. So I'm getting this. From here I can take a plus b outside, so it becomes minus 5ab, a plus b common, and inside you're left with a square minus ab plus b square plus 2ab, right? That can again be simplified as minus 5ab, and this is minus c, right, from here. So this becomes 5abc, and inside becomes a square plus b square plus ab. Great. Inside part is becoming a square plus b square plus ab, right? So now what we will see is how to find a square plus b square plus c square. So we have this condition, right? We have this condition because a plus b plus c is 0, a cube plus b cube plus c cube is 3abc is equal to this part. So that is equal to 5abc a square plus b square plus ab, right? So we get 3 by 5 is equal to a square plus b square plus ab, right? Great. We have this relation, but we have to get something else entirely. So let's try to think of what is a plus b plus c whole square. A plus b plus c whole square will be a square plus b square plus c square plus 2 times ab plus bc plus ca, right? So this part LHS is 0, so it is equal to a square plus b square plus c square plus 2 times. If I take c common here, ab plus c common, this is a plus b, right? Right. So we should be able to prove that this ab plus c times a plus b is correct. So what we can do is we can replace the c with minus of a plus b, right? So what you will end up getting is 0 is equal to a square plus b square plus c square plus 2 times ab minus a plus b whole square. So minus a square minus b square minus 2ab. So notice that this bracket becomes minus a square minus b square minus ab, right? So taking this whole bracket on the left hand side, you will get a square plus b square plus c square is equal to 2 times, will become equal to 2 times a square plus b square plus ab, right? I hope you are seeing what has to happen here. Take this term to the left hand side. So you'll get 2 times a square plus b square plus ab, and we have already found out a square plus b square plus ab, right? That was 3 by 5. So the answer for this will be 2 times 3 by 5, which is equal to 6 by 5. This was a fairly easy question. So if you are confused at some point, remember that we have first derived a power 5, b power 5, c power 5 as this. And that was a very straightforward sort of derivation. We just expanded using binomial theorem. Once we got this, I'll use this condition where I put in the a power 5, b power 5, c power 5 as this thing. And you got the expression a square plus b square plus ab is equal to 3 by 5. Actually, at this stage itself, you can take, I think, b common, and it will be a plus b. And you could convert, you could go back and reverse these steps and convert it to ab plus bc plus ca, right? So yeah, but it is fairly straightforward what I did later also. What you did was a plus b plus c whole square. So that is LHS is 0 because a plus b plus c is 0, and you get a square b square c square is minus 2 times ab bc ca, ab plus bc plus ca. And I'm just taking b c common here, a plus b, and writing c as minus a plus b again. So that will make it turn out to be exactly a square plus b square plus ab. So you get 6 by 5, which is the answer here. Let's move on to the next question. This is question 2, part 2. You have to solve the equation x power 4 minus 2m plus 1 x cube plus m minus 1 x square plus 2m square plus 1 x plus m is equal to 0, where m is a real number. M is a real number. So I'll just give you the brief hints for this question. It's not very difficult. Case 1 that everyone should look at is when m is equal to 0. If m is equal to 0, this equation boils down to x power 4 minus x cube plus, not plus, minus x square plus x plus 0 is equal to 0. Now it is very easy to factorize it and find all the roots here. X will be equal to 0, plus 1, and minus 1. So there are two roots at 1 root at minus 1, and one root at 0. So case 1, m is equal to 0, you get 4 solutions. And we have solved it. In case 2, when m is not equal to 0, in that case, this is a 4th degree equation, and I don't want to solve a 4th degree equation. I don't even know how you're going to solve it, right? There are methods, Ferrari's method to solve a biquadratic, or I think it's Cardano's method, but I don't want to do it. It's annoying. So what I will do here is convert it into a quadratic equation. And obviously, there's no quadratic that can be found for x, but there is a quadratic that can be found for m, right? So I will write it as 2xm square plus x square minus 2x cube plus 1 into m plus x power 4 minus x cube minus x square plus x is equal to 0. This is a quadratic in m. It is very easy to show that the discriminant of this quadratic comes out to be 2x cube minus 3x square plus 1 whole square. And therefore, the roots of the quadratic can be called m1 and m2, and they will be equal to, you use the quadratic formula and you will get the roots as x square minus x, comma, x square minus 1 by 2x. These are the two roots that come for m. So taking each case separately, you get two equations. X square minus x is equal to m, or you get x square minus 1 is equal to 2mx from the second root, right? These are two new quadratic equations now. So from here, I can find x1 and x2 roots of this quadratic in terms of m. And from here, I can find x3 and x4, which is roots of this quadratic in terms of m. And that will give you the answer of this problem. So you're solving, in the second case, you get, in terms of m, you get 4 different roots. In the first case, if m is 0, then you don't have to do anything and it is immediately solved, right? Great. So this quadratic is fine. So we move on to question number 3, part B. Question 3, part B is saying that a triangle with sides ABC has circumradius is equal to 1, and you have to prove that a plus b plus c is greater than equal to ABC. This is a fairly straightforward question. We will be using the basic identity that we know for triangles: sine a by 2, sine b by 2, sine c by 2 is less than equal to 1 by 8. Equality happens for equilateral triangles, and this identity inequality is true for all triangles. The proof of this can be done by Jensen's inequality. You should check out some of the other videos on this channel. I think I have done this before on my channel. You can check it out, or any standard book, you can look at it and why this is true. So we'll be using this inequality here. So the second step is obviously, like, I want to convert it to a, B, C. Now, because of properties of triangle, I know sine rule applies. So technically what I have to prove here is a is equal to 2r sine a, r is equal to 1, capital R is the circumradius, that is 1. So this proof is basically 2 sine a plus 2 sine b plus 2 sine c is greater than equal to 8 sine a sine b sine c. This is what I really have to prove. So basically I have to prove sine a plus sine b plus sine c is greater than equal to 4 sine a sine b sine c. 4 sine a sine b sine c. This is what I have to prove. I know from properties of triangle again that this sum for any triangle can be written as 4 cos A by 2 cos B by 2 B by 2 cos C by 2, and I have to prove that it is greater than 4 sin A sin B sin C. So ultimately what I have to prove is cos A by 2 cos B by 2 and cos C by 2 is greater than equal to sin A sin B sin C. This is what I have to get, right? Great. So that is very straightforward from here because I already know this, right? I want to convert it to sin A sin B sin C somehow. So let's multiply this side by 8 times cos A by 2 cos B by 2 cos C by 2, which is a positive quantity in a triangle because all of these angles are acute. I'm multiplying both sides of this inequality with this, and I'm getting cos A by 2 cos A by B by 2 cos C by 2 because 8 and 8 gets cancelled, right? And immediately it works out, right? This is double angle formula. 2 sin A by 2 cos A by 2 is simply sin A. So 1 2 goes in that. 1 2 comes with B by 2 B by 2. So sin B and sin C is less than equal to, we have proved, cos A by 2 cos B by 2 C by 2. So immediately in 3 steps we are getting this, and we know that from this we can derive it and basically convert the inequality that we have to prove into something that is more amenable. So, and we got that here, right? So it is obviously done. This is a pretty straightforward. As long as you know this, you will be fine. And as long as you know sine rule and basic transformations of trigonometry, this transformation you should be comfortable with. So this is done. Then we move on to question 5, which is about two functional equations. So the first part of it was f of x square plus x plus 2 times f of x square minus 3x plus 2 x square minus 3x plus 2 is equal to 9x square minus 15x for all real x, and you have to find f of 2011. Now whenever you have functional equations like this, obviously you have to put in some values and try to get some patterns. Sometimes when there are expressions inside the f of something, right, it is nice if you can get another equation which has a similar expression. Like right now we have two unknowns, f of x square plus x, and another unknown is f of x square minus 3x plus 2, right? Like let's call this unknown u and let's call this unknown v, right? Now we have an equation u plus 2v is equal to something, right? If by chance I can get an equation which involves u and v, some au plus bv is equal to something else, right? Then it becomes a simple equation that you have to solve for u and v, right? So that is a standard trick that you need to be aware of when you're approaching functional equations, that this type of thing frequently happens. So once you know that that thing can happen, then you are looking for a transformation that converts this to something with the same terms, right? So if I put x is equal to, instead of x, if you put 1 minus x here, right, what you will end up getting is f of 1 minus x whole square plus 1 minus x plus 2f of 1 minus x whole square minus 3 times 1 minus x plus 2 is equal to 9 times 1 minus x whole square minus 15 times 1 minus x. Now obviously this doesn't seem very easy to think. Why would someone think of this, right? But the idea will become fairly clear when we factorize this. When you factorize this x plus 1, this is x minus 1 and x plus 2. Anything you do to x, if you do 1 minus x, the thing doesn't change a lot. 1 minus x, notice that if you replace this with 1 minus x here, it becomes 1 minus x, and this bracket becomes 1 minus x plus 1, so 2 minus x, right? So this product is still the same as this. Be careful and think about that. 1 minus x into 2 minus x is x squared minus 3x plus 2. So the logic of why somebody would think of this substitution, right, comes when you think about the factorization of this. So what can I do to this? What transformation can I do so that I end up getting the same variables? I don't end up having two other f of things, right? If it was some f of x squared plus x plus 3, then I would be stuck with a new variable, right? I don't want a new variable in my equation. I want a different equation with the same u and v so that I can solve them. Now notice what happens here if you do 1 minus x. If I do 1 minus x here, it becomes minus x. And 1 minus x here becomes 3 minus x, I think. 1 minus x, 3 minus x, right? Does it become 3 minus x? Okay, I have made a mistake here because this factorization is obviously wrong. So this is actually x minus 2, and now it doesn't become 3 minus x, it becomes something nice. If you put 1 minus x instead of x here, it becomes minus 1 minus x, which is wonderful because the minus minus will cancel and it will become simply x squared plus x. So basically the question is a trick question where this transformation immediately converts this equation. So original equation is f of x squared plus x plus 2 times f of x squared minus 3x plus 2 is equal to something. After you replace it with x is 1 minus x, you just get this one becomes f of x squared minus 3x plus 2, and this one becomes 2f of x squared plus x, right? So you get the same, you get a system of equations with the same two variables. Obviously this side transforms a little more. This side eventually becomes, I will just write down the answer. Let me just check what I have solved here. Okay, I feel like I have made some mistakes in my, when I worked it out here. So I will just do it again. So this becomes 9 times 1 minus x whole square minus 15 times 1 minus x. So minus 15 plus 15x. So that is 9x square. 9x square will come. Minus 2x become minus 18x. So minus 3x plus 1 plus 9. So this is becoming 9x square minus 3x minus 6, right? Great. So you have one equation, this one, and the second equation is this one. What I will do is I'll just solve for f of x squared plus x. How can I solve for that? I have to eliminate this, right? To eliminate this, I'll multiply this by 2 and subtract, so multiply this whole equation by 2, and from there subtract 1, right? So this will become 2 times this, which will cancel this, and this will become 4 times this, which will subtract 1 time, so it will become 3 times f of x squared plus x here on the LHS, and here it will be 2 times. So 18x square minus 9x square is 9x square 2 times. So minus 6x minus, so plus 9x minus 12 minus 12, right? So cancel the 3, you get f of x square plus x is equal to 3x square plus 3x. So 3 times x square plus x minus 4. Now this is wonderful because f of something is coming in terms of that variable itself. So we can easily see that f of x must be equal to 3x minus 4. Because f of x squared plus x is becoming 3 times of x squared plus x minus 4. So then f of 2011 is pretty straightforward from here. The 6033 minus 4, so 6029 is the answer. So in this question, again, this was a trick, but only with a suitable amount of practice of such questions will you realize that sometimes functional equation questions are boiling down to simple simultaneous equations. So you have to discover during the phase of problem solving the transformation that preserves this property. How can I basically convert this to this, right? And this back to this without introducing a new variable. So this was the magical transformation that made that happen. Once you discover this, the question is fairly straightforward. Okay, and the last question that we will do is another functional equation, question 5 part 2, which was f is from n to n such that f of x square plus f of y is equal to x f of x plus y, right? Great. So if, and what do I have to find? Find all such functions, basically. Find all f such that this happens. So I will start by putting some values. Put x is equal to 0 in this, and we get f of y is equal to y for all real y. Not real y, for all natural number y. Natural number y. So that is a useful result that we have gotten. Great. Let's put x is equal to 1 and y is equal to 0, right? So what we get here then is f of 1 plus f of 0, right, is equal to 1 f of 1. So f of 1 plus 0, right? Correct. So great. So we're getting f of 1 plus f of 0 is equal to f of 1. Okay. So let's think about this 1 plus f of 0. 1 plus f of 0 will be equal to f of 1 plus f of 0, right? What property am I using here? I'm saying this is some t. Then t is equal to f of t, right? According to property number 1, right? So I'm using that property here. Now this becomes, I know that f of 1 plus f of 0 is equal to f of 1 plus 0 from property number 2, right? So this becomes f of 1 plus 0, right? Great. So that becomes simply f of 1, and that is equal to 1, right? Because f of 1 must be 1 from property 1 again, property 1 again, property 1. And this was property 2. From here to here was property 2. And notice that overall you're getting 1 plus f of 0 is equal to 1. Therefore, f of 0 is 0, right? F of 0 is 0. So we have gotten the value of f of 0. Now let's assume f of 1 is some t. F of 1 is some t. I don't know the value of f of 1. So f of 1 is t, and let's say x is equal to 1 and y is equal to f of some z. Z belongs to natural numbers. Okay. So I have this relation. Let x is equal to 1, y is equal to f of z, and z belongs to natural number. So using the first property itself, you get f of 1 square plus f of z is equal to 1 into f of 1, right? 1 into f of 1 plus y is f of z, right? Correct. Correct. Okay, I feel like I made some mistake here. F of okay. I think here what I want to do actually is f of 1 plus z. Let's think about what f of 1 plus z is. So that is equal to f of 1 plus, since z can be written as f of z, f of z, right? That is property number 1. So now I have 1 square plus f of z, right? Now look at the original identity here, right? I can write 1 as 1 square, and instead of y I have f of z, right? Now it is fitting this property. So I will replace it using this. So x is what? X is 1 and x is again 1. So this is 1 into f of 1 plus y is f of z, right? Great. So ultimately see what I have gotten. F of 1 plus z is f of 1 plus f of z for any z for any z belonging to natural numbers, Great. So that will mean that let f of 1 is equal to t, right? If f of 1 is t, then f of 1 plus some natural number, let's say 1, right, will be f of 1 plus f of 1, right? Because z is also 1 by this property. So that will become 2 times f of 1, no? So this can be extended, because now f of 2 I have gotten. F of 2 is 2 times f of 1. F of 3 will become 1 plus 2, which is f of 1 plus f of 2, which is 2 times f of 1. So it is 3 times f of 1. So now by induction, I can prove very easily that f of n is equal to t times n, where t was the value of f of 1. You can convince yourself of this fact by just taking f of 1 as t. What is f of 2? It is 2t, because 1 plus 1 will become f of 1 plus f of z, and z is 1 in this case. F of 2 will come 2t, f of 3 will come 3t, and you can convince yourself that by induction I will get f of n is equal to tn. So now what is the possible value of this t? T is still unknown. F of 1 we have not found out yet. So what I will do for that is just use the identity that we have already done. So I'll just clear the diagram here. So our identity was f of, the question itself says f of x square plus f of y is equal to f of x f of x plus y. I have already proved that f of x is some t times x, right? Where t is equal to f of 1, right? So using that, I will get f of x square plus f of y will be ty, and this will be x into tx plus y. So this will be f of x square plus ty will be t times x square plus ty is equal to tx square plus y. So this becomes tx square plus t square y is equal to tx square plus y. And tx square gets cancelled, and you get t square is equal to 1, because y cannot be 0. Y was natural number. So t can be plus or minus 1. So f of x can be plus x or minus x. We will reject the minus x because we were working in natural numbers. So the function can be f of n is equal to n. So that is the function that satisfies the equation, functional relation that we had in the beginning. Satisfies the functional equation. So here, this was slightly involved. This was actual Olympiad problem from Romania. This was slightly involved. You have to be very careful about what properties you're using. You should take a little bit of time, go back to the beginning of the problem statement and go through that once more, and be careful about each step that we have made. All the steps that we did were justified. You should revisit it if you're unsure. But this is a little slightly involved question. Practice a lot more functional equations. These types of problems are generally hard. It is hard for everyone, and if you're struggling with it, it's all okay. So that happens with everyone. You will get better with practice, and keep trying. I will be having some of these questions in the future challenges as well. I'll probably make another video for challenge number 3. If you're finding some problems that are still unsolved from challenge 1 and challenge 2, or even challenge 3, you can request for those specific problems that you faced in the comment section. Do like and subscribe to my channel. You will get more content for free in the coming few weeks and months, and it will be very instructive. That's all for now. See you next time.